Okay.
I let people in. Is that okay,
All
Jenny?
right. Yeah, sure,
Good.
sure. So hello to everybody. We'll wait 1 or 2 minutes before starting. So today we have one more session of the Logical Universalist webinar. This session is managed technically by Silvia Simonato from Springer Heidelberg, and thanks very much, Silvia. And then today the main talk will be by Alexei Muravitsky about non-monotonic logic. But of course, it's not restricted to this specific topic because his paper is developed in the general framework of the consequence relation, abstract setting, which is something which is directly related with the universal logic project. And since Alex grew up, if I may say, in the Moscow Logic School, we will have first a presentation by Alexei of this school. But now let me leave the floor to Melvin, who is a member of the Editorial Board of Logical Universalists, and with the chair of the session today. Please.
Good morning, everybody. And so we will start this morning with Alex Sitkin, who has words to say about both history and organization. Alex?
Okay, let me share my screen. Thank you. First of all, where is do you see my screen?
Yes.
Yes.
Okay, so as Jean-Yves said, today's presentation will be by Alexei Muravitsky about non-monotonic logics. So I have a confession to make that I'm not Alexei, and I know very little about non-monotonic logic. So I will not be speaking about those logics. I will be speaking where Alexei and by the same token I came from. So, oops. This is a very well-known story. When Tarski met Post the first time, he mentioned that Post probably is the only logician doing propositional logics and not related to Poland. And Post replied, "Oh, actually, I was born in Białystok, which is Poland." What I want to say is that even though Alexei's last name Muravitsky sounds very pretty much like Polish name, he has nothing to do with Poland, and he has nothing to do with Lwów Warsaw School. We came from the different background, and the Lwów Warsaw School is very well known, and there are many books and papers about the school. But actually, about the same time, there was another school of logic. And as you can see, here are kind of 4 founders of the school, being Zhigalkin, Kolmogorov, Glivenko, and Bochvar. And if you look at my screen, you see that the first paper by Zhigalkin was in 1927 about, it's actually about classical propositional calculus and formulas, and he give his machinery for doing for recognizing the tautologies and stuff like this. The very well-known Kolmogorov's paper on tertium non datur was in 24, actually 24-25 was 2 years volume. Glivenko wrote his paper on intuitionistic logic in 29. Bochvar published his paper about three-valued logic in 38, and it's actually related to nonsense logic that was discovered, so to speak, or rediscovered rather much later. So those were the founders of Moscow School of Logic. Now, in 1943, Yanovskaya founded this seminar in mathematical logic in Moscow University. Here, I need to say something about Yanovskaya, because what happened in the former Soviet Union in 30s, they decided that formal logic doesn't supposed to, is not the right logic. So it was prohibited. The mathematical logic survived only because they were pretending that they're doing mathematics. It has very little to do with logic. On the other hand, the Semyonovskaya founded the seminar that actually started the Moscow logic traditions. So it's a very unusual story. And as you can see, the first the seminar when it started was ran by Yanovskaya, Zhigalkin, and Pyotr Novikov. And over time, this seminar started in Moscow University, became a city seminar, city logical seminar. And later, when Markov moved to Moscow, he was also part of this. Here is a very rare picture. It's the members, the picture of participants. It's about 1955. And here you can see, this is Kuznetsov, this is Yesenin Volpin, Adyan, Uspensky, Yablonsky, Yanov, Muchnik, Bochvar, Yanovskaya, Novikov, and this is Shestakov, who actually published his paper on the circuit design like about 2 or 3 months after Shannon. He missed, so to speak, just by a few months. So this was the seminar that actually became a Moscow logical school of logical school. Now, the founder of scientific school in Moldova was Alexander Kuznetsov, who since 1946 till 1965 served as scientific secretary of Moscow City Seminar on mathematical logic. And he served only till 1965 because at this time he moved in Moldova. And there were 2 reasons why he did this, why he moved to Chisinau. One of the reasons being he got in trouble with authorities. And another reason was that at this time he got married and his wife was from Moldova. So they decided that for him, it will be safer if he moves to Moldova, to Chisinau. And this is how Moldovan logic school started. So what Kuznetsov did was from the historical point of view. In 40s, late 40s, he was doing research in recursive functions and published a few papers, one of which is his famous paper with Trachtenbrot. And at this time, he rediscovered Ackermann function. Then he was doing optimization of logical circuits and came with a very good approach to this. Then he was doing many valued logics, and he proved that for finite many valued logics, for each such a logic, each such a logic has just finite number of pre-complete classes. So for any n-valued logic, there is an algorithm to decide for a given set of functions whether the set is functionally complete for any finite value. And this turned into studying closed classes of logical functions in non-classical logics. I will not go into details. It's a very interesting topic. What he did actually, he kind of translated functional completeness from, let's say, matrix based to syntax based. He reformulated it. So, and he with his student Ratza they investigated logics like S4, like intuitionistics, and intermediate logics. And of course, let's say for S4, you cannot do this by regular means because the matrix is infinite, but it's finitely axiomatizable logic. Using this, you can do something about functional completeness. And also he wrote a famous paper about Scheffer-stroke, the theory of Scheffer-stroke too. Then he studied problems of decidability in non-classical logics, and primarily in intermediate logics, in which he did a lot of discoveries. For instance, he and his another student, Gerchiu, they proved that there is a intermediate calculus which lacks the finite model property. Yankov prior to proved that there is an intermediate logic without finite model property, and they proved that actually there is a finitely axiomatizable such a logic. Also, he was studying pseudo-Boolean or hating algebras, and he proved that, for example, that finitely generated infinite hating algebra always contains a finite chain subalgebra, which is very useful property. Then he started to research in proof intuitionistic propositional calculus, and this he was doing together with Alexei, who will be presenting in a few minutes, but not about this topic. It's totally different topic. And then he moved to quasi-groups and projective geometry, and this was partially because his son was interested in quasi-groups, let's say, but just partially. Maybe the other way around. I cannot tell you for sure. Here is Kuznetsov. Alexei is my advisor. And I want to say a few words about one of his papers and decidability of the general problems of completeness, decidability, and equivalence for propositional calculi. of course, this is his picture, and this is a picture of the volume where you can find a translation of this paper. The paper was published in Algebra and Logica in 1963, and the results were actually presented to Moscow seminar in 1961. So why I decided to speak a little bit about this paper, the reason is very simple. As you will see, in a way, this was one of the first papers towards universal logic. It's one of the papers when people started to look at not random, very broad classes of logics, as opposed to particular logics of interest, like, let's say, Kreisel-Putnam logic or Damet logic or Medvedev logic, or particular classes like intermediate logics or Lukasevich logic. It's broader. So this is what he was doing. So we were speaking about propositional logic. Of course, the formulas based on propositional variables. He used just these four connectives. Oops. So, and what he called regular propositional calculus is a finite list of axioms and inference rules, and two inference rules. He used just two inference rules: the uniform substitution and modus ponens. And here I need to tell something, because back then, and not only in 61, it's also in 70s, when we were talking about logics, we were referring primarily to the set of theorems rather than consequence relation. Now, when we say logic, we kind of assume that we're speaking about a consequence relation. Back then, it was a set of theorems. So, and each regular propositional calculus defines a consequence relation. And in a natural way, it defines this set of theorems as usual. And then we can introduce a quasi-order on this calculi. But as you can see, it's based on a set of theorems. It's not like quasi-order on consequence relations. But this is what we need. And of course, we can introduce equivalence, also a very natural way. And now he said, okay, let's assume we have a regular propositional calculus. So given another one, can we decide whether these two are equivalent? Or can we decide whether given the calculus is decidable? Or can we decide that one of these calculi is less than another one? And even if given that one is less than another one, can we decide whether they're the same? And at last, can we decide that with very simple questions that I is consistent, just consistent? It's nothing complex. So it turned out that all these problems are undecidable. And this explains, in a way, why there is A and C, because undecidability is the core here. So, which shows that even in this pretty broad but still restricted class of propositional calculi, the algorithmic problems are undecidable. So now, of course, when we are talking about Moscow School of Logic, I cannot not to mention one of the probably well-known representative of the school, Yankov. Well, logicians know another spelling of his last name through J, and this volume will be published sometime later this year. And I want to finish my brief presentation by making another confession that Alexei and I, we kind of deviated from Moscow traditions, and we wrote something that actually is in Polish traditions and about consequence relations in general, which also actually is directly related to universal logic. And this book is supposed to be published like in a month or two. And I want to finish this with this, my confession. Thank you.
Okay, thank you very much, Alex. Does anybody have any fast questions of Alex before we get to the main talk today? All right. Okay, well, thank you. Maybe, okay, got the screen back and our speaker.
Yes.
Okay.
Yeah.
All right. So do you want to see if you can get your screen shared?
Yes. Yes.
Okay, very good. All right, so I want to introduce the main speaker for today. I was about to say this morning, which is true where I am, but not where most of you are, I think. So our speaker today is Alexei Muravitsky. He's at Northwestern State University in Louisiana. And the topic is on nonmonotonic consequence, two modes of nonmonotonic consequence. Okay, thank you. Go ahead.
The title of the talk a little bit different.
All right.
But first, I would like to thank Jean-Yves and the board of Logic Universalis project for giving me an opportunity to express my views on non-monotony. Also, I would like to say that webinar, which started about 2 years ago, took off about 2 years ago, since then has been gaining more and more popularity, and it's a great honor for me to present my views here. So I will be discussing two ways to implement a semantic approach to non-monotonic consequence relations in an arbitrary propositional language. For one particular language, we will also discuss the proof theoretic framework that will connect with this semantic approach. This presentation is an addition to my paper published in Logica Universalis last year. Hereafter referred to as Muravitsky 2021. All main results of the last paper will be discussed, and also some new results. So we will discuss non-monotony expressed in formalized languages. All main objective languages that will be involved are propositional. Aristotle is credited with distinguishing between what we know and how we know. Georg Kreisel, who made this remark, adds, quote, "The point I wish to stress, again, as a matter of accumulated experience, is how much easier the former question is to answer to our satisfaction than the latter. Of the what, whose aspects strike the mind's eye, we have easily accessible practical knowledge, which constitutes in the threshold for additions by further theory. We also would like to know about the how, but the price is high." I would like to draw your attention to two moments of this passage. First of all, about threshold, and second point is about the price. And you will see that the price really is high in answering the second question. So we know that it is not only the possible easiness of answering the what question that prompts us to start with it, but also the view that knowing how we know is one small department of knowing what we know. This is a quote from Bertrand Russell's book, My Intellectual Development. It's worth of quoting the whole passage. I quote, "I reverse the process which has been common in philosophy since Kant. It has been common among philosophers to begin with how we know and proceed afterwards to what we know. I think this is a mistake, because knowing how we know is one small department of knowing what we know." Some time ago, it was recognized that non-monotonicity of reasoning does take place in colloquial speech. Richard Stalnaker gives an example of non-monotonic argument based on Grice's concept of conversational implicature discussed in Grice 1989. This example is remarkable only in one respect. It indicates the need to distinguish between the concept of argumentation and the concept of logic. Logic deals exclusively, in my view, with forms, while content can be involved in argumentation. Stalnaker's example is an example of argumentation. Its non-monotonic effect is based on the interaction of contents, more precisely between implicit and explicit contents. Understanding logic as a science dealing with forms of judgment, we will pay attention to sentential variables and, as a consequence, to the role of substitution, understood both as an operation and as a rule of inference. Preliminary note. Before proceeding to a formal presentation, we know that we are using the concept of logic in its dialectical and not demonstrative manner. That is, we will consider the relationship between a set of premises and the conclusions that can be drawn from these premises according to some standards. So we fix a propositional language L. Later, we will be more specific with a denumerable set of propositional variables and non-empty set of logical connectives. Unspecified L formulas are denoted by letters, Greek letters, alpha, beta, etc., sets of formulas by x, y, etc., and the set of all formulas by this symbol. Given sets x and y of formulas, we write that x included in a special way or is a special subset of way if x is a finite subset, perhaps empty, of y. The operation of uniform or simultaneous substitution is understood in the usual way. We denote substitutions in L by sigma, delta, etc. The result of substitution, sigma in a formula alpha, is denoted by sigma of alpha. Accordingly, we denote by sigma of x if we apply substitution to each formula alpha in x. The structure, which consists of the formulas and the connectives, including constants, is known as the formula algebra of type L. And taking a subset of formulas, we denote by V of x the set of all variables that occur in the formulas of x. Now we introduce mapping from the power set of the formulas to power set of the formulas, and denote by C of x the result of applying C to set x. Then we introduce a relation between subsets of sets of formulas and formulas defined through a C operator. Well, if we have a relation, we can go back to C operator in according to definition 2. So definitions 1 and 2 allow us to use relations like turnstile and operators like C interchangeably. The following properties of C operator have long been in the spotlight. See, for example, Mackinson's 2005 book. It will be listed in the reference at the end of my talk. So we have here 9 properties, and we add one more later on in the next slide. So the first property, reflexivity, monotonicity, closeness, finitariness or compactness, cumulative transitivity, weak cumulative transitivity, which is also known as cautious monotony, then strong cumulative transitivity, and finitary inclusion, which is the converse of finitariness. And strong finitariness, which is differs from regular finitariness in the following condition: if X is non-empty set, then C of X is included in the union of Cy, where Y is a finite, a non-empty subset of X. Now we have to discuss a return to what-how questions. Alfred Tarski, who introduced the operator C into the discourse in his address to the Polish Mathematical Society in 1928, began with the following remark: our object in this communication is to define the meaning and to establish the elementary properties of some important concepts belonging to the methodology of deductive sciences, which, following Hilbert, it is customary to call metamathematics, unquote. In the published version of his address, Tarski formulated properties C1, C3, And also he called C of X the consequences of the set X, which suggests to call any operator C satisfying these properties a consequence operator. In our view, it was the rich variety of contextual practices, namely practices in mathematics, in formal logic, such as like doing geometry, doing algebra, and other mathematical disciplines that prompted Tarski to introduce this notion. In his own words, the concept of logical consequence is one of those whose introduction into the field of strict formal investigation was not a matter of arbitrary decision on the part of this or that investigator. It is very natural to propose the properties C1, C3. Also, Tarski considered C4, but not other properties. One interesting property was introduced over a quarter of a century later in Losh-Sushka famous 1958 paper, namely the structurality property, denoted here as C10. Here, sigma is an arbitrary substitution. As for the what-how questions in relation to monotonic reasoning, at least with regard to its forms as presented in mathematics and the deductive sciences, it is generally agreed that the properties C1, C3 seem to answer the first question, or at least can be regarded as the threshold for additions by Fedor theory, quoted from Kreisel. Frege and Tarski can be credited for pioneering to answer the second question. In particular, Tarski pointed out the following two ways of implementing monotonic reasoning in metamathematics. According to him, the first way is as follows. From the sentences of any set X, certain other sentences can be obtained by means of certain operations called rules of inference. The second way is through semantics. In the most general terms, one can imagine a non-linguistic machinery M such that it is natural to say that the sentence alpha follows from the set of premises X when M accepts alpha whenever M accepts all premises of X. For propositional languages, this leads to matrix consequences. And although from this level of abstraction, the implementation of this idea may vary, we will not discuss here all the alternatives. We discuss these alternatives in our book, Muravitsky 2022, which will be out of print in July. At this point, little can be said about answers to the what question in relation to non-monotonic reasoning. To reiterate, we argue that it is the lack of contextual practices of non-monotonic reasoning that has led to speculating about the minimum conditions that a consequence relation should satisfy to present a bona fide non-monotonic logic. In contrast to this optimistic hope, one can see a growing confusion in the endeavor of trying to learn something about the objective world of reasoning through pure thinking. Another confusion, the what-how confusion, occurs when someone, in an attempt to give a general definition of non-monotonic reasoning, gives examples of answers to the how question. Question: If contextual practices of non-monotonic reasoning are lacking, what can the theory of non-monotonic reasoning be based on? One possible answer is, it can be based on conceptualized practices of monotonic reasoning. Recall that algebraic logic began with George Boole's algebraization of Aristotle's syllogistic. And to give credit to Kreisel's insight to answer the what question, we should simply propose a C operator that would not satisfy C2, that's monotonicity property. However, there are many candidates for answering the how questions. Not all of them are indisputable. What seems certain is that any mode of non-monotonic reasoning worth exploring should be considered together with its monotonic counterpart. To be fair, we must say that this idea was systematically implemented in Mackinson's 2005 book, although only as an explanatory tool and not as a methodological guide. Following this observation, we introduce the notation Cn to indicate that the last operator satisfies the property C1, C3, while C will stand for an operator that may fail some of these properties. However, even in the case of monotonic reasoning, if the answer to the what question can be explicated in the form of conditions C1, C3, any possible answer to the how question is fraught with danger. Here are two views on the issue. The first comes from the corner of constructive philosophy. A logical inference is a movement from certain propositions, the premises, to a further proposition, the conclusion. We still need to know which of these movements are to be called logical. Quote from Lawrence's book, Formal Logic. The second point of view sounds from the corner of proof theory. If we, quote, if we simply axiomatize or define the notion of logical consequence with the understanding that a logical consequence holds when this follows logically, exclamation mark, from the axioms and the definitions, then one may rightly say whether anything really is achieved. A quote from Pravets. Pravets' 1974 paper. Such sentiments sometimes, though rarely, appeared in the camp of researchers of non-monotonic reasoning. Quote, what is wanted is not a specific technical definition for a specific non-monotonic logic, but a general account of what consequence is supposed to mean, of what concept some specific technical definitions is trying to capture. And one should expect such an account to explain why it is reasonable to call the concept by the name consequence. Unquote, a quote from Stelnaker's 1993 paper. Apparently, David Mackinson, in his 1994 paper, was the first to propose a clear criterion for the logicality of non-monotonic consequence. Namely, he formulated that for two operators Cn monotonic and C presumably non-monotonic, the operator C is logical, his term, if the condition 3 is fulfilled. It should be clarified that any standard on the logicality of non-monotonic reasoning is an answer to the what question, not to the how question. In formulating such a standard, we want to prescribe the conditions of what we expect non-monotonic consequence to be. Now let's consider Mackinson's conditions for logicality closely. To facilitate the analysis of tree, we introduce two relations similar to one. So we have for turnstile, which I will call turnstile, we have condition 4, and for the snake relation, we have condition 5. So so we find that Mackinson's condition is too strong. So let's first consider this inequality. So it can be expressed as the following implication, or in a shorter form, it can be written like this. The last implication does not look convincing. It is rather unjustifiably specific. Turning to the inequality, second inequality, that is writing in the terms of turnstile, we have the following implication, and we notice that there are some generalization of the above implication seems to be more flexible. Well, 7, as we'll see, is an attempt to make the relation snake somewhat monotonic. As we'll see later, in some interesting models, 7 does not hold. Nonetheless, as we will see in the sequel, limited monotonicity can sometimes be achieved in non-monotonic consequence relations, although on a path different from 7. So we call a non-monotonic relation snake logical relative to a given monotonic relation turnstile if it satisfies the conditions 8 and 9. And this is our answer to the what question about non-monotonic reasoning or non-monotonic relation. Conditions 8 and 9 can be reformulated in terms of operators Cn and C as L1 and L2. This is minimum requirements. Now we have to take a look at on the map of the properties I listed before. So I divided these properties in 1, 2, 3 in colored group. The first property is C1 is this group consists of one property, which is reflexivity. Then closeness group consists of one property, closeness. Monotonicity property group consists of C2. Cumulative properties include C5, C6, and C7, and finitariness properties consists of C4, C8, and C9. So before moving to the next slide, I want you to focus on section 3 and section 4. Section 3, section 4, and section 11. Also, we can notice, looking at proposition 1, that blue group and green group do not interact in the sense of these implications. They do not interact at all. Blue group is cumulative properties, and green group is finitariness properties. So if we want to target C2, we should expect that other properties can be affected. Regarding C1, C1 is always satisfied if the consequence relation in question is logical. So we also observe that the cumulative properties, what I said, infinitarianous properties do not interact. In the mode of non-monotonic reasoning that we are about to propose, thereby answering the how question, the closeness and cumulative properties that have been the focus of non-monotonic research will fail. Therefore, we will be interested in infinitarianous properties. But even in this case, by proposition 1, section 11, we cannot have both infinitarianous and infinitarianous inclusion because they both imply monotonicity according to proposition 1, section 11. So we, as expected, we choose C4. Now, turning to formal part of my presentation, we consider a system M, which consists of algebra of type L and a subset of the carrier of the algebra, and we call this system logical matrix. Any homomorphism from the algebra, formal algebra to A is called evaluation in A and also in M. So the result of evaluation V to L is denoted by V brackets alpha. And we say that evaluation V validates alpha. And if we have a set of formulas, we denote V bracket X brackets X as result of applying evaluation V to each formula of X. And we can say that, okay, that's later. So then we define what is called, oops, sorry, M consequence, or I will say single matrix consequence. To pronounce it's for any evaluation V if V validates all formulas of X, then V validates formula alpha in M. Also, if we have a set F of non-empty non-empty set of matrices, we define X implies set M alpha if X implies single matrix M alpha from each M from the set M. You will call it set M consequence. So we have the two monotonic consequences, single matrix consequence and set matrix consequence. So it's well known that any operator C and sub set M satisfies the conditions C1, C3, and also C10. And this is famous proposition which goes back to Lukashevich and Tarski, 1930, theorem 3. And modern expositions can be found in Wojcicki's book, 1988, or Dan Hardegree, 2001, and also in upcoming book by Sitkin and Muravitsky, 2021. In order to move to non-monotonic consequence, we define restricted valuations. So suppose V is a subset of variables, and we say that valuation restricted to V is simply a mapping from V into carrier of A extended to homomorphism. And by this symbol, we denote the domain of B. So using this concept of B restriction, we can reformulate M consequence as follows. If we have a matrix B, we can define M consequence in terms of restricted valuations as follows. If for any restricted valuation V with the domain V of X, if V validates of all formulas of X, then for any extension W, extension of V with domain covering the variables in X in alpha, W validates alpha. David Mackinson, in his papers 2005 and 2007, proposed to use the next definition as a new type of consequence. I call it a single matrix restricted consequence because it uses restricted valuations. Suppose we have a matrix M and X restrictive M restrictively implies alpha if for any restricted valuation V with the domain V of X, that's variables occurring only in X. If V validates X, then there exists an extension W of V with the domain covering variables in X and alpha such that W validates alpha. And this relation is called M-restricted consequence, or MR consequence for short. Mackinson defined MR consequence only for the case when M is the matrix based on two-element Boolean algebra, and called this relation logical friendliness, and we'll discuss logical friendliness later in the last segment of my talk. So then we denote the corresponding operators as C sub R sub M and C sub R and sub set M. So we define them in the usual way, and then we can ask the question whether the newborn operators are logical with respect to the corresponding monotonic operators, and the proposition 3 claims that they are logical. All are logical. What about other properties? Well, if the CR set M is logical, it's reflexive. What about other properties? When we regarding other properties, C sub R sub single matrix M may fail C2, that's monotonicity, and may fail all cumulative group, the properties of all cumulative group. Well, this example shows that if a restricted valuation validates P, it can be extended to validate not Q. But if we add Q to the premises and restricted valuation validates P and Q, it cannot validate in Boolean algebra, it cannot validate not Q. Also, this relation based on the two-element Boolean algebra is not transitive. And for this reason, the closeness fails. It's not resonant because of this argument. So we also have that closeness fails, and property C6 also fails, as it can easily be seen. If P is subset of PQ, and PQ can be follow both P and Q follow from P in restricted mode, but not Q belongs to the difference, and for this reason the property C6 fails. And since C5 implies C6 and C7 implies C6, both C5 and C7 fail in this model. Well, however, there is a problem with restricted consequence. Let's consider algebra A, which is implicative algebra, and consider matrix with the single designated element. So we can see that in this matrix, P restrictively implies Q, but P and Q implies Q does not imply restrictively Q for the obvious reason. However, what we added is a tautology in matrix M. And also we can add any formula alpha to keep consequence which doesn't contain Q. Well, this drawback, we should do something with this drawback. Of course, we can notice in this example that Q in some sense is not essential variable. We can replace it with R, any other variable. So this is the idea behind the next definition when we define M essential variable in a formula. So the idea is that, well, the definition goes as follows. So P, variable P in alpha is called M essential. If there are valuations V and W in M such they give different outputs, although for any Q different from P, V of a Q equals W of Q. So otherwise P is M inessential, M essential. So we have a set, we can extend this definition to a family of matrices. Well, and also if we have a matrix M, we need to extend this definition for a set of matrices. If we denote the set of essential variables in set X, essential M essential by this symbol, but we also have to note that variable can be M essential in one formula in X and inessential in another formula. So we have to collect only essential variables which are essential somewhere. If they are inessential in other formulas, we don't care. We include them as essential. Now we adjust our definition of MR consequence to definition MR star consequence, which is defined as follows: that X restrictively star M implies alpha if for any restricted variable with domain limited to only essential variables of X. If this valuation validates this set, then there is an extension of V covering variables, all variables in X and alpha, which validates alpha. Now, what is, well, we can generalize this to any set M of matrices. But what is set X sub M? Well, this is a trick. So we, since our this consequence depends on M, we select any element in the carrier of M, algebra of M, and introduce new constant and add it to language L, and then require for any variation to interpret this new constant as A in M, of course. And then we define C sub M instance of alpha when we replace each inessential variable with C sub A. Well, I denote this, call it C sub M instance, not C sub A instance, because the choice of A is irrelevant. What is relevant that we do it everything in M. And then we define X sub C sub M when we collect all alpha C sub M where alpha is in X. So we can notice that all essential variables in X are exactly all variables in X sub Cm, and this observation will help us to reduce MR consequence to MR star consequence. So what we have here, we introduce two operators, C sub R star sub M and C R star sub set M. So in the usual way. And then we can notice 11, which can be proved by using the previous observation. So what we can notice first, that this operator is less than or equal to C star sub star sub R star sub set M. It's almost obvious. And example 2 shows us that the other inequality is not always true. But the second question, and probably more important one, is if the newly born, newly defined consequence relation is logical. It is logical relative to corresponding monotonic M consequence. Well, all the results of example 1 about the failure, the monotonicity property, and all cumulative group the same, because in those examples, we all the variables in the premises were essential, M essential. Well, relative to this matrix, M sub B2. Now we have to go over other properties. In particular, we want to investigate monotonicity in non-monotonic consequence relation. So we call the relation weakly monotonic if the following condition is fulfilled. So it happened that for any set M of matrices, MR consequence is weakly monotonic. What about monotonicity for M R restricted star consequence? Well, the result is not that impressive. First of all, we cannot go over any set of matrices. we have to restrict ourselves with a single matrix. Even for a single matrix, we have only this limited result. So if X is a subset of Y and the essential variables X, common variables essential in X in alpha are the same as M essential variables in Y and alpha, then this implication holds. It's quite less impressive. Now, let's go over finitariness. So we define a relation very strongly finitary if it's not only strongly finitary, but also the Y, which is a non-empty subset of X, satisfies this property. If we have a matrix, a finite matrix, and MR single matrix restricted consequence is very strongly finitary, but this is the first part of this proposition 8. But also, if Z is a superset of Y with this condition, then Z also restrictively M implies alpha. As a corollary, we obtain the property, the following. If M is finite set of finite matrices, then set M restricted consequence is reflexive, weakly monotonic, and very strongly finitary. What about a restricted star consequence? The result is less impressive, as should be expected, because everything is tied to a matrix, given matrix. So we have the following. If X M restrictively star implies alpha, then there is a non-empty, and X is non-empty, then there is a non-empty subset Y, such that this condition is fulfilled, and M restrictively implies alpha, and also if Z is any superset of Y with this property, then Z also M restrictively implies alpha. So here we have only very limited result. If M is finite set of finite matrices, then operator C sub R star sub set M is reflexive and strongly finitary. Strongly finitary, not more than that. Historical remark 3. David Markinson in 2005 and 2007 papers established strong finitariness of logical friendliness in the form close to the one in proposition 8 with slightly weaker condition on Z. Now I would like to, well, the mathematics behind this is not very deep, and it basically can be reduced to one definition in one proposition. And then I use this proposition. I even didn't number it. The subtitle for this slide, I called it the kitchen. This is how Lewis Sakio used to call the techniques behind. So definition is the following. So if M is a matrix, we have a non-empty set X of formulas and valuation V in M. We say that V adapts X in M if there is an extension V, W of V, with the domain which covers the variables in X and in V, which validates all formulas of X. And then we can prove the following proposition that X single matrix restrictively implies alpha if and only if for any v sub v0, which is the common variables in x in alpha, if this valuation adopts x in M, then the same valuation adopts alpha in M. And this is the main tool we need. Now I would like to make a couple of remarks about substitution. In substitution for, if we fix a matrix M, matrix consequence is structural. This is very famous result by Losh and Sushka in 1958 paper. My question is about structurality of restricted M-restricted consequence and M-restricted start consequence. Of course, we cannot expect that structurality will have place here, but something different related to substitution does hold. So, but not without additional restriction. So we can prove 12 with the restriction that X and alpha do not have variables in common. This is very strong restriction, of course, but the counterexamples show that if we drop the restriction, we don't have it for both for a restricted consequence and a restricted start consequence, which can be generalized for any non-empty set M of matrices. But everything must be providing this condition only. Well, so far we did not specify objective language, but now we'll do. Moving to logical friendliness, we introduce logical connectives. These logical connectives and a constant top, which will stand for true. We know this language by L. Sokol, and you know the formulas by A, B, C, etc., and sets of formulas by gamma, delta, and etc. So since all our models matrices will be Hoytian algebras with the greatest element one, we require for any evaluation in this matrix, we require the condition that V of constant top equals 1. Now Mackinson defined logical friendliness. We know this relation by Snake sub f as follows. This is his definition. And in parallel, we can define relation Snake sub f star using this matrix restricted star definition. So according to what has been said before, we have the compound inequality 16. And the legitimate question is if we have something in between. Well, if we have something finitary and non-monotonic. The answer is yes. Such an operator exists, and it's discussed in my 2021 paper, but in that paper, I didn't discuss whether that operator is logical with respect to Cn sub M sub B2. Well, it is logical. It can be proven that this operator defined in this paper is logical. It's worth of mentioning an unsuccessful attempt to find such a consequence between these two. Well, I took, instead of 2-element Boolean algebra, I took a Boolean algebra. I tried to, and then define a restricted consequence. And then I found that this restricted consequence is the same as logical friendliness. Nevertheless, proposition 10 will serve us as a navigator for further systematic development of the theory of non-monotonic operators. Now we attract intermediate logics. And so Alexei said that this is different from intermediate logics, but not exactly. In one point, intermediate logics enter the game. So we denote by int and CL intuitionistic propositional logic and classical propositional logic, and all logics in between, logics in a demonstrative sense, as a set of formulas closed under substitution and detachment or modus ponens. All these logics are called intermediate logics, and the set of intermediate logics is denoted by this symbol. And we don't care at this point whether it's lattice, Hoyting algebra, or whatever. So we don't care about this. I need this notation only to refer to intermediate logic. That's as a set. So we, in a usual way, we define L derivation from a set gamma that in a usual way, if we have L derivation, if each of the formulas is either element of gamma or belongs to L as a set, or can be obtained by modus ponens only from two preceding formulas. So in this particular sequence, if it's L derivation, we say that the last formula is derived from gamma or L derived from gamma. And then we define in a very usual way and call this relation L consequence. And we define also the corresponding operator, Cn sub L, and we notice that this operator is monotonic. And also we need the notion of a Cn sub L theory, which is gamma is called Cn sub L theory if it's a fixed point with respect to this operator. Then we introduce something new. We introduce new symbol which doesn't belong to our language, it's extension of the language, and we call this formal object sequent. Next, we define sequential L calculus for each L in intermediate logic L. So we define using CL axioms and rules, and we will have three more rules. But I want to draw your attention that all CL calculi differ only by axiom 4 when we have L derivation or L consequence. All other rules and axioms are the same. We have 4 more rules. In the previous rule, we have a reverse substitution. And then we have cut, not without a condition, but under this condition. Also, we have deductive replacement in antecedent with this condition, and deductive replacement in a consequent. So then we define sequential L derivation, derivation of a sequence in a usual way. Using rules and axioms, and we say that the gamma, well, arrow, big arrow A holds in sequential L calculus if there is sequential L derivation ending with this sequence. So we then define L-based consequence using the SL calculus. What's the motivation for this definition of SL calculi? Is the following proposition 11, which shows that logical friendliness is complete with respect to classical logic based calculus consequence. There's completeness, basically it's completeness theorem. Then since we already have not one consequence, we have to check the properties. And first we can check the reflexivity property. Then we can it can be proven that non-monotonicity monotonicity property fails. That's each L-based consequence is non-monotonic. And also with this condition, it's strong finitary. But with this condition, the condition is very strong. It means that gamma and A do not have variables in common. But this is our price. Remember the price mentioned by Kreiser. This is our price for answering the how question. And also it's clear that the difficulty lies in the lack of semantic for any CL L-based consequence. There is no semantics. Now we'll think or speculate on the semantization of C-based consequence. So I have to use some terminology from our book with Alexei Muravitsky. So we can notice that, well, each L consequence is a unital and assertional. If it's unital and assertional, we can define for each consequence, we can define Lindenbaum-Tarski algebra relative to each theory D of L consequence. And then we notice that each of these algebras, which it can be regarded also as, well, each algebra is Heuting algebra because we use intermediate logic L. And also we can regard it as a matrix taken for the filter theory D. So we have Heuting algebra with a designated element, and in this algebra, this element will be the greatest element. And in case of classical logic, each of these algebras is a Boolean algebra. And if we use the following equivalence 19, which is discussed in as proposition 6.3.5 in our book, which will be out of print in July, we can, this allows us to use L-based consequence as M sub L consequence for particular set of matrices, which are this set of these matrices. In particular, if we have L equal to classical logic, we just have this equivalence. But remember, in one of the previous theorems, each of these matrices or each of these algebras is Boolean algebra, and basically it doesn't. We do not leave the scope of friendliness, logical friendliness. However, we can use this idea as a navigator, and we can move to other consequences related to any logic L. And here I can limit myself with two conjectures that each L-based consequence is M sub L R consequence. And also we can move to M sub L R star consequence and define L based star consequence, and then formulating it through gamma sub C, where gamma sub C is obtained from gamma if we replace each inessential variable in this algebra. In this algebra, we replace each inessential variable with a constant top, which is very convenient. So we remember that each of these algebras is Haughton algebra. And then we have, I want to formulate conjecture 2, that L base star consequence also M sub L star consequence. That can be defined not only through calculus, LCL calculus, but can be defined in a using matrices. Now I'm closing to my conclusion. I would like to, I started with a philosophical discussion. I would like to end with philosophical discussion. So we started with discussion about the concept of non-monotonic reasoning. And popular belief says that time may render the final verdict, which consequence, which definition is good, which is not so. But what is meant by saying this? We can suggest two possible answers. One answer is follows from the quote from Richard von Mises' book, Probability, Statistics, and Truth. And he wrote, quote, "I aim at the construction of a rational theory based on the simplest possible concepts, one which, although admittedly inadequate to represent the complexity of the real processes, is able to reproduce satisfactorily some of their essential properties." The second opinion is more difficult to express. I think that success of proposed approach is often provided by unexplored space for its further development. The larger this space, the more questions left unanswered. The more tools available to answer these questions, the more likely it is that this approach will become the main focus of research. Such an approach could be termed open, that's open for further research. This opinion of ours echoes another statement by von Mises from the same book, quote, "The value of a concept is not gauged by its correspondence with some usual group of notions, but only by its usefulness for further scientific development." To be open in the above sense means not to be sterile in the understanding of Georg Kreisel, who wrote, quote, "Aristotle gives much attention to the matter of choice of abstractions. This indicates a shift of emphasis away from matters of principle, for example, mere validity of analogies, to a focus on, of course, valid cases, which provides safeguards against sterility, not merely against straight error. Quote from Kreisel 2029. Whether a consistent approach is open enough to avoid sterility can only be judged by time. In a broader context, concerning the what and how questions, the difficulty of the task should not overshadow the more important level associated with knowing. This thought is not mine, but a paraphrase of the thought of Thomas Aquinas, who wrote, quote, when something is more difficult, it is not for that reason necessarily more worthwhile, but it must be more difficult in such a way as also to be at a higher level of goodness, unquote. If you replace knowing instead of goodness, you will understand what I mean. This is my reference list to this talk. Thank you very much.
Well, thank you very much. I think if people have questions, perhaps they could raise their hand, you know, their virtual hand.
Should I stop sharing?
Yes, I think so.
Or people may ask about the slides.
Well, then we can come back to them.
Okay.
All right. So do we have questions?
Yeah, we have one guest, Ian Wolensky.
Yeah, right.
I have a question about such constructions like deduction theorem in non-monotonic logic. Because, you know, task is consequence operation is divided into two kinds of axioms, general and specific. And you didn't say anything until friendliness about this special axiom. And one of them is deduction theorem. What about in non-monotonic logic? I mean,
It's
supplemented by connectives, of course.
No, it's not connected. So, so my purpose was first to outline the what question. What for Tarski, if we put Tarski's conditions in this framework, conditions C1, C3 answer the what question, and to implement the conditions, it requires more to be more specific about language. If we use deduction approach, a syntactic approach, if we use a semantic approach, we also have to can be more specific about connectives. If we want to develop our, which I did in the first part, the develop an approach regardless of connectives or logical constants. So we don't have any deduction theorem. So deduction theorem is out of this framework.
Does that answer your question? Other questions? Oh, Ursula?
I am under a big impression about regarding the presentation of this talk and the content of this talk. But I have some question about terminology. What, in your opinion, is the consequence? In human thinking, consequence is always relation or operation monotonic. And I didn't find an example of reasoning which is not monotonic. And if you can give some example of a situation when we can use non-monotonic reasoning, I will be very grateful. Because in my justifications of operators of consequence or consequences regarding reductive reasoning, deductive reasoning, inductive reasoning are monotonic. Thank you.
Okay, so that's the problem. I think that's the problem of non-monotonic reasoning. For monotonic reasoning, how it appeared in the history of logic was based on what I call contextual practices, starting from Aristotle, and then picked up by Tarski and Frege. They used mathematics as a pattern, how to proceed in a logical way, and all their endeavors were based on mathematical practice, not on in mathematics in different disciplines. What can we say about non-monotonic reasoning? Most of the examples are known in the literature. They use non-monotonic arguments, like the story, Tweety story, and other stories. Like Stalnaker's example, they use arguments, non-monotonic arguments. It's not logic. Well, then people go to build logic, just regardless of Tweety's story, they build logic, and there are different logical systems. But what's their goal? There are two questions. What question means that we need to formulate standards? And then how question, how can we implement these standards? And this is what I call what, how confusion. Instead of answering the what question, the first example of answering what question was Mackinson's suggestion to call non-monotonic operator or any operator C logical if it satisfies such and such equalities. I think without these prescribed conditions, our work in non-monotonic reasoning area is hanging in the air. Philosophically, it's not justified. It's justified for monotonic logic and was justified by Frege and Tarski.
Thank you. I have another question.
Formally, all my patterns, MR consequence is example of non-monotonic reasoning, but not for colloquial speech situation.
Thank you, but I don't know if I am satisfactory for your answer, but I have another question. You introduced the notion of weak non-monotonic, weak monotonic, and strongly binary. What is the connection between monotonic and weak monotonic and strong finitary and finitary, and what is the application of these new notions?
Well, I don't know about applications, but very strongly monotonic, very strongly finitary means strong finitary with some monotonic smack. There's some monotonic smack in the theorem. At the same time, it's not weakly monotonic. Weakly monotonic, it's weaker than monotonic. And all MR restricted consequences are weakly monotonic. But when we go over finitariness, weakly monotonicity, not exactly as it is. It's a little bit different.
Thank you.
Because when we find Y, we take supersets Z, which include Y, only Y. We're talking about only Y, with additional condition on the common variables in Y and in alpha and in Z and in alpha.
And your approach to non-monotonic consequence is a semantic approach.
Semantic approach, this is the first part, but then I show that we can also build syntactic approach, starting from a logical friendliness, and then we move to other intermediate logics. Because logical friendliness is basically classical logic, and we can move to intuitionistic logic, to any intermediate logic. Well, the problem is that there is no semantics there, and without semantics, it's very difficult to investigate the properties. And I made an attempt to build the semantics, but it just formulated two conjectures.
Yeah, thank you.
There's a question in the chat. You might want to take a look at it and
Yes.
try addressing it.
Well, I don't know who's asked the question. There's a similar question to what Ursula asked. If non-monotonic reasoning exists in research. No, non-monotonic system exists. But how they illustrated in colloquial speech? There is no good illustration. Tweety story, if you know this Tweety example, Tweety is an ostrich or a penguin. If you know, maybe this story, no? Well, this is argumentation. Tweety is a bird. Almost all birds fly. Therefore, Tweety flies. But then we'll learn that Tweety is a penguin or an ostrich. And our, consequence, we cannot make the same consequence that Tweety flies. But it's not logic. This is tied to the contents. It's argumentation, yes. It's non-monotonic argumentation, but it's not logic. Logic deals with forms. Argumentation deals with forms and contents. That was the problem in Stalnaker's paper, when he tried to formalize the distinction between inner and outer contents. I think that's the right term, David. So you remember the difference, inner and outer contents?
I've forgotten what was in Stolniker's paper.
You was a reviewer.
Yeah, but that was a long time ago.
Okay. Yeah, a long time ago. Yeah, but formalization was very clumsy. It almost with no. I don't know who picked up this research. Even Stalnaker himself didn't do it. It was an attempt to formalize in a logical way in the way of forms. It didn't go anywhere. But example of non-monotonicity, it's probably using Grice's implicatures is very good when we have different contents, inner content and outer content. It's example of non-monotonic reasoning, but not non-monotonic logic.
Maybe I could throw in a question here on a different direction. Are you familiar with what's called strict tolerant logic?
Which logic?
Strict tolerant.
No.
Okay. It began with one example, and I've since shown there are infinitely many. It's the original logic was a three-valued logic, but with two designated sets, a strict designated set and a more tolerant designated set. And X was a consequence of S if whenever all the members of S were strictly designated, X was tolerantly designated. One of the curious things about this is the original example had turned out to have the same consequence relation as classical logic, but they differed at the meta-consequence level. So it leads into the question of to what extent a consequence relation determines a logic. And then it turns out there are actually infinitely many examples of that nature. But I was wondering if anybody had looked at something like that in non-monotonic logic, where you have a stronger and a weaker notion of designated value.
Okay, well, anyway, we have to formulate standards. What we, as in classical logic, as Pravitz pointed out, and Lorenzen, without standards, what can we say? For monotonic logic is more or less simple, because we look how we do mathematics, and we arrive at Tarski's properties, and we can say, okay, well, that's enough. Well, we can add finitariness, compactness, or we can do without compactness. And all mathematical systems, I mean, not for informal logic, in informal mathematics, they satisfy C1, C3. Maybe some other properties, but we take C1, C3 as a standard. And the same we have to do for non-monotonic logic, consequence relations, in order to call them logical.
All right, all right. We have another question here, Jerry Chandler.
Yes, I thank you very much for this very, very interesting talk. I found it to be quite exciting in terms of my own interests in this context. So I have a couple comments first, and then perhaps a question. And it has to do with our host's comment about designated terms and what that might mean. And I would say that number one, it seems to me that your work overlaps to quite some extent in its conclusions with those of Charles Saunders Peirce and his notion of relatives and how relatives are related to numbers, and his use of the notion of indexes in creating his examples, both within his notion of graph theory, as well within his notion of semantics of naming of objects. And his naming of objects, logical objects arrived at by deduction, is rather unique in logic, as far as I know, at that context of designation of terms using an index. So this part, I think you might find of interest to look more closely at Charles Saunders Peirce's notion of graph theory and how he used inclusion and exclusion to determine the truth and falsehood of statements. Now, this is more than a century ago, and you might find much of this to be quite obsolete from modern perspectives, but I think it might be useful. Secondly, I would suggest that perhaps the basic logic of both chemistry and genetics depends upon this sort of meta logic, if you would, based now on the atomic numbers as being constants. That is, the chemical table of elements is a set of constants. It's an enumerated set of constants. And this enumeration of the constants is self-referential in the sense that the notion of an atom has a self-reference to both the nucleus of the atom and to the electrons of the atom. And these two numbers are equal. They are of the same count value. So it's the same count value of the nucleus and the electrons gives them a very special relationship, logical relationship, when you form a vinculum or a collection that is gathered together into a whole. And this is definitely something that is unique to the logic of chemistry and genetics, and might be a useful example for you. I don't know. That's speculation on my part. It's very, very conjectural that it might be useful to you, but who knows? Okay, so thank you very much.
Yeah, I would like to, if you send me a reference to Charles Peirce's work, of this particular work, I would like to read it. As to the other comment, so there, when you have substitution applied somehow, then you have logic. If you don't have substitution, just irrelevant to substitution, I am reluctant to call it logical.
So a marriage between a man and a wife is not logical?
No, of course not. We're talking about formal logic. Formal. Form is the main word in the idea. Form.
Well, you have quoted Aristotle and his notion of form.
I quoted Kreisel, not Aristotle.
Well, okay, I'm sorry. Yes, you had quotes from Aristotle, and for Aristotle, he noted the distinction between formal, material, and efficient causalities, leading to theological conclusions. And I would think that both the sciences of chemistry and genetics and the logics that they have developed are definitely in the category of material causality, and are not, and hence have a different notion, or not a different notion of formal, but a natural form that includes the atomic numbers and the logic of the atomic numbers. So yes, there's a problem there, but it's something that could be addressed.
Well, there is informal logic, which studies informal argumentation. I study formal logic and formal argumentation.
I understand.
For me, logic is only formal.
Pardon?
For me, logic is formal. Other types of logic, they can be argumentations and theory of argumentations. And there are different argumentations and studies of argumentations. But for me, logic related to forms of judgments.
But
not
yes.
in Aristotelian Aristotelian sense, but form of judgment.
How do you relate this notion of formal judgment to geometric judgments?
The same. If we can formulate it, well, in geometric, we have mathematics and logic. As to logic, we have formal logic. We can use second order logic. Well, it's about forms.
I find that to be a very, very narrow definition of form, but that I understand what you're saying, so that's fine.
Well, as I say to my students, science is very narrow field. We always start with restrictions in any science, any discipline.
I'm a hardcore realist.
Science is very restrictive. Oh, I mean, this discipline, any discipline is restrictive. Science is restrictive as a whole.
I'm a very hardcore realist. I'm sorry.
Well, I'm afraid realism is breaking in here. But I've just had a message that we're at the 2-hour point.
Okay.
Perhaps, David, do you have a very short thing, or is it?
Yes, I'll try to be a very short comment.
Okay,
I don't think,
and then I think we'll stop.
I don't think it's really acceptable to say that a relation is logical only if it's structural, in other words, closed under substitution. Look at the relation of consistency between two propositions, classical consistency. That's certainly just as logical as deducibility, but it is not closed under substitution. It's not structural.
I agree.
Perhaps the best way to look at logical friendliness, I think, is as looking at a curious logical relation, which is weaker than consequence, but roughly speaking, stronger than consistency. And it tends to be rather irregularly behaved, have only, very roughly speaking, the kinds of properties which are shared by those two relations. And I'm not sure whether it's a very good idea to try to see friendliness somehow at the heart of the theory of non-monotonic relations in general. That's all.
Well, first I agree with that. Structurality, well, there are consequence relations which are not structural, of course, but they are also about forms. As to logical friendliness, it's a starting point. When I proved the completeness and realized that I can formulate it syntactically using classical logic. Instead of classical logic, I can use any intermediate logic. What's good about this? Why not any other logic? Well, we have possibility to build good semantics using Hoyting algebras. That's
okay. I think we're going to have to stop here. Genevieve, do you have concluding remarks?
No, I just want to thank everybody for participation, the speaker, Alexei, yourself, Mel, and Springer managing. And I would like to say that we will go on with Logical Universalist webinar next week with a session about a book which was recently published about the square proposition. So have a nice day and see you next week.
Okay, thank you.
Bye-bye.
bye-bye.